now let me summary what I did last time. Okay, at least try to write. So, in summary, so first, right, we wrote that scalar fields, at least at the end of the lecture. We wrote that scalar fields, and then we just wrote this guy, right? Cubed on square root of 2 omega p, right? And then AP e to the I k x plus, let me write cc for this time at least. And anyways, AP dagger, right? And then e to the minus I direct p is p I px, okay? And then the momentum were just the derivative of this, right? With respect to t. Then we defined the momentum field, right? And then we showed the commutation relations, right? In the end, we said that, okay, these two guys, let me write y in here, these two guys were 0 for equal time commutation, and this guy giving the commuting nature was this. These were the summaries at least, so let me just then write the for any operator. We also have this equation. We wrote this equation also, right? This is H and O for any operator O. Or what I mean by operator is this pi's and pi's and any operator that we can define for this equation at least. And then, what was our aim? We try to write the Hamiltonian, right? If we write the Hamiltonian with respect to these two fields, right? Hamiltonian density we said, and when we took the integral, we said it is Hamiltonian itself, but I will just drop density term. I will say Hamiltonian, okay? And then we just use the definition of infinite harmonic oscillators, right? In harmonic oscillators, and then rewrite the Hamiltonian in terms of P, AP dagger, okay? I will do this now, at least. And then to construct, the construction of this quantum scalar field theory was just acting on a Fock space, act on with this, the Fock space, so that you can construct all the states and everything, okay? So this was the main thing that we did, and then we said that in the end, we just try to establish that A QFT, you can misunderstood, but just give it. A quantum field theory is just, right, quantum mechanics, and write QM, with an infinite number of harmonic oscillators, one for each momentum, right? Or let me write wave number. P. Then we conclude with that. So now I will just start from the perspective of Hamiltonian, and I will try to show, at least fastly, try to show that we can write them in terms of these harmonic oscillators creation and annihilation operations. And then I will show that this guy is actually exactly looking like the harmonic oscillator Hamiltonian, okay? That we see in the classical theory. It looks like that, at least, okay? Let me just raise this button. So, okay then. free Hamiltonian for scalar field was right? It was just Hamiltonian 1 over 2 d cubed x, let's say, space integral, right? And then the square root of momentum field, square of the momentum field, and then this guy, the gradient square, we said, and then this guy. It was really same as the energy that we write for the Hamiltonian in the classical setting, if you remember. We just quantized these guys, and then we wrote the quantum operators that correspond to these guys. And what we will do now, we just replace them in, so that, and by using the commutation relations, we will just try to define this in terms of APs and AP daggers, okay? We will do this, so let's do that. Okay. So firstly, let me just restate phi and pi simultaneously, okay? Let me just write it like that. So this d cubed k over, okay, 2 pi, 3 to 2, 1 over square root of 2 omega k, okay? And then I just do some trick, okay? I'll just do some trick, and that trick corresponds this using this negative modes, okay? And then I will just write this like that. What I did just was basic, okay? I just take k to the minus k, and when I take k to the minus k, this ikx becomes positive, the minus sign, and I bring a k to bookkeeping this term, so that I can write it as easy as it gets, okay? Then the momentum is just a derivative of it, so I can just write that, okay? I will try to fastly show this. Maybe not do all the calculations, but the calculations are really easy. You can write them very easily without any problems. So let me just at least try to write them. Right? Okay. So what we will do is basic. We will take this, okay? Take the gradient of it, like this, the spatial derivative, and take this. You know this guy too. Take the square of it, take the square of it, and we already know this guy. We will just replace everything inside, and then we will try to make them simplified, okay? This is all it is. It's really algorithmic, so I don't want to go with the algorithms, okay? It's really algorithm. Just replace, substitute there into that, okay? So maybe let me at least write 1 or 2 terms from here. Maybe I can write it in here. Let me just show p squared term at least. Okay. So now we have 2 pi's, right? One momentum and another momentum. To take the integral, we need another bookkeeping, right? This k, we need another thing. K prime, k, p, it doesn't matter because there are 2 of them. We need to distinguish which one is what, okay? So basically, we just write this. Let me start. d cubed k, okay? And let me use primes. d cubed k prime. And then we have what? 2 pi 3 over 2, 2 pi 3 over 2 again, okay? 2 of them. And then exponentials, there is ik and ik prime with the x, so I just add them, okay? So that's easy. That's just that. K prime x, and then I just multiply them, this is x, I just multiply them with omega k prime over 2. 2 is out of the square because there are 2 of them, square root of square, right? Right here. That's all. And then they are just the multiplication of these 2 guys, okay? Okay. AK plus, no, AK minus, AK dagger, okay? And then AK prime, this is minus K, let me not write it wrong, AK prime minus A minus K dagger, okay? And then you just multiply these guys and put them all together. And then let's just substitute this into here. And we should do for all of them, okay? And in the end, we will find the result. So, let me just argue about this term in here. You see this is spatial derivative, okay? So, it will hit to this guy because we just compose them, right? And it will just bring down a k. And when it brings down a k, there's k and k prime, right? Two k's because phi squared in here. Where is it? Okay, this guy. There are 2 of them. So k dot k prime we will have, okay? For every derivative, and there is a square, and we will just substitute them all. And in the end, we will find something like this, okay? Let me just show it to you now. We will write something like this. H will equal to, okay? D cube k, right? And then divided by 2 pi cube, okay? Then, wait a second, okay? Let me just write omega k over 4, okay? And 2 in here, a k dagger plus a minus k dagger, a minus k minus, okay? We will find this. So this guy is invariant under this k to the minus k places. So I can just take this side, not forget about this side, take this side and shoot down to the plus k. Then I will just use the commutation relation. As you remember, let me just write the commutation relation for neutral number. K, A, okay, K, this is not prime. Oh, this is prime, yes. And this will equal to what? Something like this, K minus K prime, right? In that sense. So we will just use the commutation and we will replace it and then we will turn them so that we will find this late form, okay? This final form will be looking like this when you do all the calculations. They are really straightforward, okay? So A, K, dagger, A, K, okay, plus 1 over 2, 0. That's all. So, do you remember the form of the Hamiltonian when we have it, right? Do you remember that? It's the same. So, when we work with this field theory and we try to just replace the field theory in terms of node functions that are corresponding to harmonic oscillator, okay? We just took them, replaced them, and in the end we will see that this complicated form reduced to this simple form. And now we can just act on a state, let's say, and we can find some, let's say, if we act on this, this will annihilate this, and then we can find its zero point energy with the infinite spatial volume term in here, okay? It will be infinite, but there are some regulations, and it's easy at least for the flat spacetime, okay? For curved spacetime, there are some more sophisticated renormalization schemes for doing that, but at least for flat spacetime, we know how to do it, okay? So, by starting that, at least, we show the Hamiltonian, okay? So we can just stop it in here, at least for the Hamiltonian, and we can come to the discussion that I said that this is somewhat relativistic theory, the field theory itself. Maybe we can find some non-relativistic regime in that relativistic field theory, and if it is truly the quantum field theory, that should reduce to quantum mechanics in non-relativistic regime, right? Otherwise, why we are doing this, okay? It should be. So, let me show it to you now. Firstly, if you remember, we said that field phi creates a particle at a point x, okay? So we have to restrict our definitions, our states, to single particle states so that we can just seemingly find the Schrödinger equation with the relativistic corrections, but we will say, let's forget about relativistic corrections and then we will find Schrödinger equation, okay? So let me just write it. So, let's try to find the first quantized. Okay? first quantized. What I mean by first quantized is quantum mechanics. Okay? First quantized version of that second quantized. What I mean by 50, right? Second quantization means we are trying to quantizing fields. Okay? When you quantize the fields, you just say second quantization, but we are not quantizing the second time. Okay? It's just semantics. Okay? Don't just think of it. The first quantized is quantum mechanics, the second one is quick shifting. Okay, that's all. So now we have to restrict ourselves to single particle states. Okay? Let's do that. So let me pick a basis. Okay? A basis is in that sense simple. Let me just write it like this. It's a basis, okay? Cat basis. Like that. So we know that we can just this is like a particle at point x, and we know that the field phi, if you remember, this guy, when it hits the vacuum, it creates a particle at point x. So I can just take them out, right? I can just write it like this then. This is the first thing that we know about this. Also, this all what we did was in Schrödinger picture, okay? We can just we can just go on to the Heisenberg picture. Now we can just go to the Schrödinger picture, okay? How can we go to Schrödinger picture? You just need to define the wave function, and the definition of the wave function is something like this, okay? Now, what we know is, we can just pick this phi out. Again, you can pick the phi out, okay? Then you can, similarly, you can write it like this, right? Now, what we know the definition for field phi, the field operator. We just replace it in there, okay? We just replace it in there. But before that, okay? Before that, we know that the Schrödinger, the form of the Schrödinger equation, right? We have a time derivative and the space derivatives and some of that. So maybe we can just try, okay? We can just try to say that I can just take this guy, time derivative of this guy, like this, right? And this corresponds to what the time will go inside, okay? And then we will have this. As I said, when I write this x, it's x and t. It's like this, okay? But in shorthand, I'm just writing like that, okay? If I'm doing otherwise, I will tell you, okay? Otherwise, you can imagine that there's x and t. We can write it like this. So, what we know is the Klein-Gordon equation we found, right? This guy. You know that. Is 0. Okay. Then we can use this also to write it as it is, right? This is dt. Okay. dt squared phi 0, right? And then this phi. Okay, just keep that in your minds. And this guy. Now, we can just do this. We just take the derivative, we know the definition of phi, we can just replace phi inside. Okay, we can just replace the phi inside and try to find the final form. So, let me just try to write it in here, okay. So, I, 0, okay, del t phi, and then it's psi, okay, and it's psi there. So, I can just write it like this. Firstly, 0 starts from here. Then integral d3p, okay, we know that. We know this guy. We have to write it, okay? And then we just take the derivative, right? So there is some dp in here. Why? Because the term e to the I px was the four-dimensional term. So inside this px, there was this, right? Omega pt minus what? P dot x. I'm taking time derivative, so Vp comes down. Okay? So I just write Vp then. Okay, let me just write that. Minus omega p, you'll find this term. Epx, okay. AP dagger, right? Plus omega p, right? E to the minus IPX again. And AP, and these all will hit to this. Now I just took derivative in that sense, okay? So, as you know, in the definition, I forgot to write. In the definition, the p over, right? What is that? 2 pi cube. There was this 1 over square root of 2 omega p term, right? So now it comes down, it comes up, right? I can just write it like that then. Let me just show it to you. So, firstly, also let me just write this. What's that Vp term? Vp is square root of, right? P squared plus m squared. You also know that. Okay? I showed it last time. So we have this Vp. I can expand it like this. Also this guy in there. It is in squared form. Right? Okay. Yeah, nice. So I just take the total Vp term out, and I will bring it here, and I will redefine this as phi. Okay, this is all it is. So let me just write it. What happens is this. I just take total Vp out. Let me just write it like that. Okay. Maybe it should. Okay. Vp out. Like this, okay? And then you know this piece follows from the same thing. So this piece, in that sense, is the same as phi. This is phi. Okay? So let me just rewrite that now. Thank you. Okay. So now I know what Vp is. It's in there. Okay. 0, I have it, right? Square root of p squared plus m squared, right? And then this phi I have again, and this guy. Okay? It came from this derivative term. It brings down a p squared plus m squared. Okay?
Çağdaş, can I ask something?
Yes.
How did you take that omega out from the integral? It's a predefined quantity.
Okay, you are right, I guess. I took Vp out, and we define it like that from the integral. Maybe I can answer it with a bit. Let me show the results and we can talk about it. Okay? You are right, but the result comes quickly from that perspective. I don't know why, but Schwartz did it like that, and I didn't think on it. I'm sorry. Okay? Let me just tell you.
So AP turns one particle state to a vacuum, and then you get the multiply that by ket to get the WP out. Isn't that what is?
Can I do it again?
The AP operator turns the one state into a vacuum state, and the creation operator turns the vacuum state to a like zero state.
Yeah.
So that's how you can take it out. You can if you do the math.
You say it doesn't matter.
Well, there's an integral in here, he says. He says there's an integral
Yes,
in
but
here.
you move the ket inside, bra and ket inside. That's how you can do it.
How to move the bracket inside? What do you mean by that?
Just move the zero ket to inside and phi ket to inside, and the AP in the phi turns it into a vacuum state, and then that gets 1, and IPX integral becomes a direct delta function, and then you integrate that out.
Okay. Okay. Anyways, let me continue, then we can discuss it. Okay? So, the thing is, the p squared term it's just I with the derivative and its square root. Its square will become, okay, this guy. So I just take derivative with I and psi like this, okay? And then I just took it out with like that. That means I have this term, okay? I have this term. Okay, like that. And then there's again psi. So in the end, we found this, right? In the how I did it, I just took it out. This phi hit that, and again I have psi, and then there's a time derivative of psi. In the end, I have this equation. Okay. So what is this? We can just assume that mass is really large. Okay. And then we can just do the expansion to find this term. Okay. We can just do the expansion to find this term. M minus 1 over 2. What I did, I just take the m squared parentheses, right? M squared comes out as m. And then 1 minus this over m squared. If m is really large, I can do the expansion. There's a 1 over 2, 1 over 2 comes down, okay? And then I have that, right? This term. Okay. So, square this. And then plus O 1 over m squared in the order. And again, I find this. Okay? So this is basically, there's an m, it looks odd, but this is basically mc squared. I took c as 1, so this looks like m. So if I just do that, if I just say that, okay, mc squared in the non-relativistic limit doesn't matter, I can just take care of this out, and in the end, I can truncate it in the form of like this, okay? I, delta t, I guess there's no square here, delta t, phi, x, will correspond to this guy. Which will correspond to Schrödinger equation, okay? So, when you do all these calculations, you will see that the scalar field theory with the operations, with the calculations, will correspond to Schrödinger equation in non-relativistic limit. So this hints on that what we did before was right, okay? At least we can reduce the theory into what we already know and what is already established by experiments, okay? The Schrödinger equation. We can find it in the end. So, now, let me just start with this quantum field theory in expanding universe, okay? So, QFT in expanding universe. For the model of expanding universe, okay, we will use this Friedmann Universe. So, let me just start with the subchapter, let's say. Quantization of scalar field in curved background. You can see, I'm just saying that quantization of scalar field in curved background. This is not the quantization of gravity. This is the quantization of scalar field in fixed background. In fixed curved background, okay? You please do not misunderstand that this is just full quantum gravity. It's not. It's just some trials, let's say, okay? But really good trials. We find really nice results from studying quantum field theory in curved spacetime. We learn a lot what the real quantum gravity is from this, okay? So scalar field quantization can be simplified in Friedmann Universe. So let me just write the Friedmann Universe metric. You know this, we have this metric element, ds squared, okay? ds squared is just dt squared minus a squared t, okay? And then we have this flat side. Okay? This is just dx squared plus dy squared plus dz squared, okay? Just for every xx, you have xx, x, y, and y, and it goes. You are just Einstein summation convention, okay? So, this metric is really important, at least for cosmological purposes, and also knowing that the space is now just expanding, the quantum fields tells us a lot about the nature of what would happen if we have full quantum theory, at least, okay? So, firstly, this a squared t term is explicitly time dependent. This is somewhat problematic because it means that when the time changes, things change, okay? It's not like this flat space-time setting. Something is different, but the beautiful thing is, about this Friedmann universe, we can find a transformation, that with that transformation, we can write this metric as if it's conformally flat, okay? As if it's flat, let's say, but it's conformally flat, we say, okay? What I mean by conformally flat is this. When you do a transformation to a metric, okay, the transformation should be up to a space-time dependent scalar, okay? This is conformal transformation. If you can manage to find a transformation to a metric, that after you do that transformation, the metric is looking like some function multiplied with flat spacetime, then that means that this spacetime is conformally flat, okay? Conformally flat. It's flat spacetime with some multiplicative function, okay? You can think like this. This conformal transformation is also angle preserving. They are really important. The light rays are just behaves like flat in there, okay? You can just write the scalar field theory with respect to this conformal transformations, and you can make it look like canonical, and we will do it now, okay? Let me just erase this part again, and this part. And let me show it to you, okay? So let's define first, as I said, conformal transformations. This is conformal time, okay? The conformal time is defined like this, dt prime over, okay, at prime, like this. What you will do is basic. You will try to find a transformation that when you take derivative, plug in, it will give you something, okay? And this is our current transformation, and if you do this transformation, the ds squared term, this term in the Friedmann universe, now becomes this expansion parameter now depends on conformal time, okay? Eta mu nu, dx mu dx nu, okay? Like this. Now, as I said, okay, you see here, there was this g mu nu. When you do the transformation, okay, it become some function multiplied by this flat spacetime. So we said that this is conformal flat in that sense. So now we have this curved background, scalar field theory in flat spacetime. We wrote it like this, right? This S was this 1 over 2, okay? This 4-dimensional element, and then just this guy. Right? We just write it like this for the flat spacetime. Okay, but this is somewhat misleading because there was some other terms, right? There are square root of g in here, there are just g mu nu in here, but since it was eta mu nu, the determinant of eta mu nu is again 1, so it's trivial, we don't write it, but when we change the background, we have to change the form of the action too, okay? And the form of the action for Friedmann, then right like this, is just that. 1 over 2, it should be at least looking like this, okay? d for x, right? And square root of g, okay? But we picked the other side, okay? Square root of g, g mu nu, okay? And down mu phi, okay? And then minus m squared phi squared. This term, this squared. Okay, this term. This is scalar field theory, the short background. Now for the elements of the metric, we have the action will follow, okay? So if we try to just take this, we know what g mu nu is, we know what the determinant is, okay? So the inverse g mu nu is look like this. the square root of g is just a to 4. Okay? If you just place in there and do the calculations again, you will find in the with the conformal scalings, you will find this. Okay? You remember that we wrote the action as if we split these guys, okay? We are doing the same again. So, now we have this form. So this form looking good. It looks like flat space-time. Yes.
Can we add more terms to this? More terms to this with like gravity?
More terms
Like-
to this guy?
Yes, like maybe not the richest color, but the other stuff that comes to.
Yeah, you can, while you are using this action, you can add anything you like.
No,
But we are just working on scale field.
No, but specifically scalar fields and more terms related to the scalar fields and this scalar field only.
Yeah, you can add any order. But
And
as
interaction terms, but like
Ah.
other types of stuff, can we? Like, for example, like something like a cosmological constant term or something?
For this, you
Yes.
say? Yeah, I guess you can.
But that's encoded in the metric.
Yeah.
If you have like
Yeah, but
cosmological
okay.
constant, A will be exponential.
It's like okay. There will be some terms like this, right? R cube, I guess, minus R cube, in ds, ADS, right? So with the cosmological constant term and with that there was I guess some R. I'm not remembering its exact form, but it's something like this. 3 lambda R3 or something in the metric. In the, I guess, DS universe or ADS universe, okay, of course you can do that. But for our case, with our metric, now we don't have this cosmological constant in that sense.
Okay.
And if you add that, it's just going to change the zero point energy. Nothing else. Because there's no gravity dynamic.
Yeah.
Yeah, can. But
It will just be.
should we just
zero
look at
point
the
energy.
general, most general thing we can write? Like we, I don't know. I'll do it and can we put it in?
Okay, no problem.
So what I mean is just this, okay? We are just what we try. Let me just restate what we are trying. Okay, we are trying to write the same scalar field theory in the curved background. So we are not adding anything, but for our curved background, we chose this Friedmann Universe. Okay, with respect to the Friedmann Universe, the same scalar field theory corresponds to this guy. Okay, that's all it is. Okay, so now. This, okay, it's good, but it's not good as if it's the flat background, okay? So we can maybe try to define some auxiliary field, okay? Some auxiliary field that corresponds to A theta. And with that auxiliary field, maybe we can make this section looks like the flat one, okay? Because our main idea is we need to write it in terms of the canonical form, but this a squared makes us problematic. Okay, so we try to define a new auxiliary field so that maybe we can make this action in the canonical form, and maybe it looks like the scalar field, the flat scalar field. Okay, so when you just pick this auxiliary field and replace it inside, okay, I'll just write it very fastly. Replace it inside, what you will find is this 1 over 2, okay, and this d cube x, d eta, okay, and then chi square minus this chi guy again square minus m square a square, okay, minus a double prime over a, and then this chi square. That's all. So, when we do this transformation, we try to define phi while using this guy too. When we just make the multiplication and rewrite this, okay, in respect to chi, we will find this section. So as you see, this section is really looking like this flat action, okay, really looking like this, but there is some problems. The problem is this guy. You remember, for the flat one, there was this m squared. But now, there is something else, okay? We can define it like m. Let's say this m squared again. But it's not like the mass that we know. This is a time-dependent mass, okay? So we just write it as m effective, okay? This is an effective mass in that sense, okay? So we just redefine it, right, at m effective. So m effective is, in that sense, m squared, a squared, minus a double prime over I, or a, and that's it, okay? So, what we see is this. This chi make this action looks like in the flat Minkowski spacetime, but with a time-dependent mass, okay? So everything is the same, but now we have a time-dependent mass, so it will have a large implications when we try to find the dynamics in the quantum scalar fields, okay? So, let me just write. The quantization of free scalar field phi in the Friedmann universe, let me write it like this, okay, is equivalent to the quantization of free scalar field chi in Minkowski form, okay, four-dimensional Minkowski space, with time dependent mass. Okay, this time-dependent mass portion will bring a lot of complications, and it will bring a lot of new stuff to the theory, okay? Even for the simplest theory that you have. Okay? So, let me just, okay, we have this and we have this in here, so I can just break this guy. If you try to find the equation of motion for this action, okay, this thing in classical, I try to find the equation of motion. I just take the variation, okay? From the variation, there is 1, 2 down. This 2 down cancels with this guy. There is now x in derivative in conformal time 2 times. And again, 2 comes down. And again, this 2 comes down. These 2's are cancelled anyways. And then we have this x prime multiplication. Take the total derivative and put the other one outside. Now, we have this x double prime with the variation of x, okay? So, this is the same for this guy. So, if you try to take the variation, you will find this simple equation. So, this equation is really similar to what you know, okay? Let me just make, okay. What you know in your harmonic oscillator, okay? So, if this is m effective of something like this x, there is some x double primes, and this guy. If this guy wasn't there, okay, let's say, it looks like it. So, but in other case, this guy will help to show us the, let me say something like spring constant in the harmonic oscillator case, but for our case it will be like the wave number or something like that, okay? So let me just try to solve this equation, okay? By expanding chi in Fourier mode, as we did last time, okay? Just expand it in Fourier mode. Chi now is just this, okay? I'm just expanding, okay? X with eta. Eta is now our time, but it's conformal time, okay? Eta, and it will be just easy. I'm just decomposing by the Fourier mode. I'm just decomposing the space and time components like that. You can imagine it like that. Okay, it's like looking like separation of derivatives. Okay, in that sense. Now I just decompose the time as the function. So if I just take this, if this genuinely solution of this equation, if I just take this and replace it inside, it should give me 0 in that sense, right? So I'm just taking it and placing it inside, and I will find this equation. Okay, double prime. Now, you will see something familiar from these modes, okay? From these modes. I just forgot the mode K, okay? So, you will see something familiar. Okay, what happens? I just expand this Fourier mode, okay? In terms of Fourier modes. And I have this IKX portion. I just take this, put it inside, okay? This X double prime comes from here. X double prime act from this guy only. I have two primes from here, okay? Then, this gradient, like the spatial derivative you say, this spatial derivative will act on this guy, okay? It will bring K in that sense, okay? And then we have this. And in the end, we have, this is square, in the end, we have this equation. Because why? There is this M effective in here and chi. Everything is the same. It's inside the integral. I just put it inside and find this equation. You see this omega square term? This omega square term is just now this omega square term. Okay? It is K square. Let me just write K. Maybe K will be confusing. Let me write kappa. Kappa M effective square. So this is M effective square. This is where kappa square comes from. I just write them together and write with X, and I find this harmonic oscillator equation for the mode functions for the scalar field theory in curved spacetime. Okay, that's all. I just write them. So we find this harmonic oscillator again. Okay, but now there is a big difference because the frequency is now depending on time. That's really problematic if you think. Okay, because the energy is now constantly changing with time in that sense. So last time when we tried to define this, right, define this vacuum state, we just said that okay, vacuum state is the lowest energy eigen value or eigen function of the Hamiltonian. But now the frequency is depending on time, and we see that we have some problems. We will have some problems to define the lowest energy state. And we will see that the lowest energy state is actually ambiguous depending on the observer, okay? We will see that from this perspective, this frequency depending on conformal time, we will have some ambiguities in where the vacuum is for which observer is, okay? So, now, I know this guy, I can just do the calculations then. Okay? Firstly, I can just declare that let's pick chi as let's pick chi as real. Okay, I can just say that, and also I can just expand this chi in terms of this. You remember this a's, right? A's and some mode functions b. Okay, I can just do that. Let me just do it. I will just write the expansion then. This modes can be written as like this. Okay. Like this. So I can just expand it in terms of modes, mode functions. They are truly mode functions. They are truly independent of each other. Okay, you can just check their Wronskian. Wronskian will be not zero, and you can say that they are independent actually. Okay, no problems with mathematical construction in that sense. So when we do this, now, okay, we just find the mode functions. We just find chi. We know this k, this guy. We just take this and place it in here. Okay? It's now good. Why? Because there's minus k in here. I can just write the exact form as we did for phi. Remember for phi, right? We can write the exact form. This guy is here, there. I just place it in here. I just expand it, and I will find it. Okay? But the problem is now, unlike phi, we have this time-dependent mode functions. Okay? This time-dependent mode functions now, in the Hamiltonian, from the derivatives, will bring new terms to our Hamiltonian. So the harmonic oscillator Hamiltonian will change now with respect to these V's, VKs, okay? So, but other than that, we are just good with it, okay? We have now a new scalar field. The scalar field have time-dependent mode function like that. No problem, we have this, okay? And we can just quantize it, as we did before. We can just say that, okay, let's write the quantization. I can declare it, right? Again, as we did it before. Okay. So, the basic one is this chi, that is x, okay? Eta is implicit, okay? Again, chi, y, again, eta is implicit. This will be 0. Also, this for the pi's, okay? Will be 0 for equal time concave in that sense. And the pi will be the same. Again, the quantization procedure in that sense is the same, but the results are truly different, okay? As I said, chi is implicit. And then I, x minus y, okay? This is. So I can just say, okay, this is the quantization. Now, as we did before, from the action, we can find, from the Lagrangian, as I said, we can find the Hamiltonian, right? But we already showed that the form of the action is the same of the scalar field theory in the Minkowski spacetime with just this time-dependent mass. So I can just write the same Hamiltonian in the Minkowski spacetime with time-dependent mass. It's the same, okay? No problem with that. So maybe I can erase this part or that part. I'm not sure. Maybe that should say. Okay. Let me just erase this part. So the Hamiltonian in that sense now 1/2 d cube x. Okay, nice. Momentum squared, again, as you know, this guy squared, and then plus, now M effective squared, chi, okay, squared. That's the Hamiltonian. So, if you take this mode, this Fourier expansion, replace it in there, you will find in terms of modes, the Hamiltonian in terms of modes, okay? And you can do it, of course, but let me just firstly write the chi as it is, okay? Now we have this, right? We have this, we didn't have it back then. Okay. Okay. These two. We have this guy. Now, if you take the time derivative, let's say, what I mean by time is conformal time. When I take derivative, these terms will contribute then. Okay, these terms will contribute. As you see, we now don't have this 1/square root of omega p terms because it's included in here. Okay, it's included in there. Because if you remember, this omega p term comes from those guys, so I just take it aside. You can't take it like that. Okay. So this Hamiltonian, okay, this VKs should obey at all times for all VKs to be to good mode functions. They should obey this harmonic oscillator equation, okay? Vk double prime plus omega k squared, omega k equals 0 for all k. And also, we already know that we need a normalization, okay? The normalization will be written like this for this guy, okay? It basically comes from this Wronskian term. This is basically Wronskian itself, okay? And we will normalize it to 0. So let me show you its basic Wronskian. It's not a good place to write. I can raise the C now. So the imaginary part of Vk prime Vk, okay, this guy, will be just Vk prime Vk this minus Vk this over, okay, 2I and we will set it to 1. To normalization. Okay, to do normalization. We'll set it to 1. So, but now we have some problems. So the problem is, we have this normalization, we set to 1. We finally found our mode functions. These are the mode functions. But the normalization scheme, and with this equation ruling all of them, it is not enough to completely fix the form of this, okay? As you can say, right? You can just say, okay, these are mode functions. Now I just hit to a particle. I can create a particle, and all the particle created from this x, chi, from this chi, will be in the A basis, okay? Now it seems like it, right? We have some like an observer, okay? Observes with respect to this form, with this lettering, with this creation and annihilation. But these VKs are not the unique solution, because this normalization is not fixing it. So we have to write the other solution as well, okay? The other solution is basically, if this is a solution, let's say, their combination is also a solution, okay? So I have to write it too. Okay. So let me just write this new solution as U, okay? Alpha k, nice. It's dependent on eta, okay? Let me just follow with eta. Alpha k, vk eta, okay? Eta, and beta k, vk star eta, okay? This is again a solution. If this is a solution, this is again a solution. Only if and only this normalization follows. The only way to this normalization is following is that I should take this, place it inside, and I should again find 1. To do that, the condition is this. This condition is really similar what you see in basic quantum mechanics, right? So in quantum mechanics, I will give the analogy, but if you have this wave function, right, it just goes like this, waveform. It will hit, some of it will transmit, some of it will reflect. It gives the same transition amplitude, okay? If you fix the transition amplitude 1, then this reflection will be found with this. So you will see the creation of particles will somewhat looking the same with this quantum mechanical analogy. It's a simple analogy, but it's just an analogy, of course, not a truth in that sense. It's just a way to understand these things, okay? Again, if you do this, then this condition will be satisfied, and you again have the same normalization for this guy, okay? So, now, there is some problem right now. Because if we have a new solution, we can recitate, we can rewrite this chi in terms of our new solution. Then we can expand it again in terms of new solution, and let me do that, okay? This chi, again, let's say, first time I solved this, I didn't find this, but I can find this too, right? This is again a solution, maybe not this, but this one. So I can expand it with respect to this solution also, okay? Let me just do that. Okay? With respect to this solution, I can just do the expansion, okay? And then, same thing will follow, same exact thing. UK star eta, but now there's something different. The set of creation and annihilation operators now should be rewritten in terms of these modes, right? So I have a new set of creation of annihilation with respect to that. So I can just write BK then, okay? And then I can just write this guy too, right? Like this. So now something happened. For the new solution, the Kurtz spacetime, okay, because of the Kurtz spacetime, we have this time dependence issue. Because of that, when we try to fix it, we see that the normalization condition is not enough to uniquely fix the solution. So we have a new solution. With respect to that new solution, we have new creation and annihilation operators. It's like having a different observer, right? Now there are two different observers in that sense. So what will happen? I want to find the vacuum, right? How can I find the vacuum? I have a vacuum, let's say this will hit, okay? Let's say this will, I will say it's A vacuum, vacuum A. And this A vacuum, when it hits, it can be annihilated, or one particle created at a point. But also, there is another observer. This observer sees another vacuum that is defined with respect to these creation and annihilation operators. These are, let's say, B vacuum. It will hit to that too. So now, in first, we have two different vacuums in that sense. So how can we just distinguish them? We can at least, you know, if we have a coordinate system, if it's truly a coordinate system, if there's another coordinate system, there should be some charge transition map, right? Something like that. We can just find a transition map so that we can just move between these two vacuums, these two laddering operators, okay? And we come to that point. Ve bu bükülmeden dolayı, çevredeki bükülmeden dolayı sen rotating black hole'un volümünden böyle bahsedemiyorsun. Elipsin volümünü yazamıyorsun. Şimdi black hole'un volümü nedir tartışması çok fazla var. Bunu bir yerlerden bulmaya çalışıyor insanlar. Sadece termodinamik üzerinden bulmaya çalışıyor, kuantum efektin gravity üzerinden bulmaya çalışıyor. Bu effective action principle üzerinden de bulunabiliyor. Pressure üzerinden çıkarımlar yapabiliyorsunuz. Üzerine çok daha önemli şeyler bulabiliyorsunuz. Yani bayağı black hole çevresinde kuantum efektler nasıl davranıyor bulabiliyorsunuz. Şimdi bu çok önemli. Siz burada pressure var dediğiniz anda, tamam mı? Termlerin bazılarını pressure olarak interpret ettiğiniz anda pressure'ın önündeki dv volüme tekabül ediyor.